All right.
All right, everybody. Chief Meteorologist Josh Knight here at WACH. Sorry, we're getting started a little bit late, but as you can see, had a lot to get set up for today. So thank you for tuning in. Ideally, again, I want this to be as interactive as possible. We've got Brett holding the camera and taking care of everything. He's going to be reading me your questions if you guys have any, and helping me show you a lot about air pressure today. So again, thank you for tuning in. We're going to talk about air pressure kind of in a general sense. Got some fun ways to show it to you, but also what it means for our weather on a day-to-day basis. So let's get right into it. When we think about air pressure, it's kind of a weird idea because we can't really see air pressure. So that's what we're going to try and do, is show it to you. But you might have to look close here. These are a little tough to see, but basically you have to remember that even though we can't see the air, there's a certain amount that's in this room, in your house, in your bedroom, and then depending on where you are, sometimes there's more air or there's less air. You think about it this way. We have to remember that air is actually made up of tiny invisible air molecules. And the same amount of space here in this cube can either be occupied by just a few air molecules, or on the flip side, you could have a whole bunch of air molecules in there. So low pressure is going to be when we have less air inside the same size space, and then high pressure on the flip side is going to be more air floating around and filling up the same size space. So that's kind of the big picture when it comes to air pressure. I want to show you how we can know, and one way that we can see that we have air pressure in this room right now. We talked about this last week. The air pressure in the atmosphere is about, on average, 15 pounds. Sitting on top of my head, on top of your head, it's pushing in every direction. Again, we don't really feel it or really notice it because it's been there ever since you were born. When you notice it is when it changes. That one's for later. When you are maybe going up really high in a building in an elevator, your ears pop, or when you're driving through the mountains and your ears pop. But what we're going to do is prove that there's about 15 pounds of air pressure in this room. Now, I hope this one works. All you need is a glass, some water to pour in the glass, and then the best thing you can use, unfortunately I could not even find one, is an index card. All this is actually a piece of cardboard from a box, a 12-pack of soda. So what you're going to do, put your water in your glass. I would do it over the sink maybe, just in case it doesn't work out for you the first time. You can water in here, there's air in here that we can't see, and we've got air pressure around us in this entire room. All we have to do is cover this. The trick is covering it with something that's nice and flat. Mine looks like it's been a little warped because I was testing this earlier. But hold it on there nice and tight, and then flip it upside down. You might get a little bit of water that leaks out, so that's why it's good to do this over the sink. But as long as I've got this on here nice and flat, I'm not sure it's going to work this time, you can see, oh, we lost it. The water stays, or should stay, in the glass. Let me try with this one. This one might be a little bit better. But the reason the water is able to stay in the glass is because the weight of the water pushing down on the cardboard, or hopefully for your sake on your index card at home, is balanced out by the air pressure in the room. So let me try one more time. Hopefully you guys will have a little bit better luck at home with whatever you have as your piece of paper. But let me see here, get a nice seal on it, and then take away my hand. Looks like we're gonna get it for a little bit. So the air pressure in this room is actually pushing up on that cardboard at the same time that the weight of the water is pushing down. One other reason this works really well is because that little bit of water that escaped at the very beginning that kind of helped us make this seal, it actually leaves a little bit of a vacuum in here. So there's actually lower air pressure inside this glass than there is in the room. So if you see this picture behind me, let me switch to this side, kind of gives you the idea. The weight of the water is pushing down, but meanwhile air pressure from in this room, that 15 pounds of air pressure, is actually pushing up at the same time. You see this one is lasting a long time for us here, so that water's still in there. When you try this one, you can do some different variations that kind of make it pretty cool. You can try cold water versus warm water or hot water, see if that makes a difference for you. Or you could try doing this with a plastic cup or a paper cup. Now, what we know is that the air pressure is pushing up on this thing right now, holding it in place. Looks like it's just about to fall. If you use a plastic cup or a paper cup, what happens is the air pressure is pushing on the cup too. So that's what might play a little bit of a part into what happens there. This is an easy experiment. Again, I use a little piece of cardboard. The best thing is probably an index card. You just need something that's a little bit stiff. So let me get back here to the graphics. We've got a whole bunch of other stuff to show you. We've got our air pressure in the room, the weight of the water pushing down, and again, that's an easy experiment. Gravity's pulling down on the water, and then the air pressure in the room, again, is what holds that card up in place. So it's a really easy way to prove that in this room, even though we can't really feel it, there is air pressure pushing on us right now. So how does air pressure play into the weather? Brent, do you need me to move this stuff out of your way? You okay? So we've got high pressure, low pressure when we talk about those on weather maps. Now in general, the easiest way to think about it is that high pressure wants to go to low pressure. If the atmosphere all over the world could have it its way, it would all be equal. It'd be the same temperature everywhere, it'd be the same air pressure everywhere, but because the sun unevenly heats the earth every single day, we're always going to have areas that are hotter, areas that are colder, and areas that have high and low pressure. So high pressure wants to go toward low pressure. You can kind of see it there. That's kind of my visual to remember that. And again, the atmosphere would rather everything be equal. We would call that equilibrium. So what the atmosphere is always trying to do is get to that state, make everything the same. Again, that's never going to happen. The North Pole is never going to be the same temperature as the equator, and this here is part of the reason why. So high pressure flowing to low pressure, a good way to kind of remember it, to picture it, oh, let me back up there, is going to be if you think about it as a waterfall. We've got high up on the waterfall, that water tries to flow down toward the bottom, toward the low end. So high pressure going to low pressure. So what happens in the actual atmosphere? We've got high pressure trying its best to go to low pressure, but there's one thing that throws a big kink in that happening. High pressure can't just go directly to it. What happens, instead of moving directly from high to low, the air is forced to turn to the right. The reason this happens is because the Earth is rotating. So the Earth is rotating. We call this special force the Coriolis force. That one's pretty higher on the scientific edge of things, but that turning of the Earth forces our high pressure, instead of going right to low, to actually start to spin. So it takes this right-hand turn around high pressure, and on the flip side, when we're going around low pressure, we get the opposite flow. You can see these arrows spinning in opposite directions. So for us, when we're talking about the forecast, this is a really big part of how things come together. So let's put it onto a map. High pressure versus low pressure. And Brett, if you have any questions or anything, please, you just shout out.
Just make sure they can hear us. I'm not sure if they can hear us right.
Is it a little...
I think so. We can keep going. Okay, we'll see.
Cool. So we've got our high pressure versus low pressure on the map. So what that means for us is that we were just talking about this. The high pressure air wants to go over toward the low pressure, but it can't. On its way there, it starts to make that right-hand turn. But as it's leaving that area of high pressure, the air is leaving. So something has to go in to fill in its place. So what happens is air sinks in from higher up in the atmosphere. So what we get in effect here is a sinking motion in the atmosphere. High pressure, the air is trying to go away, trying to get. Last week when we were talking about the clouds, to make clouds, we need to get lift in the atmosphere. We need something to take the air up higher in the sky. This is completely the opposite. High pressure, the air is sinking down instead of lifting up, so we end up with sunny pressure, kind of the opposite. As air is trying to go to the low pressure to raise it up, it makes that right-hand turn as well, and we end up with this counterclockwise flow around it. Now on the flip side, all of this air is coming into the low pressure system, but it doesn't have anywhere to go. It can't go down, so it starts to go up. And that's the lift that we were talking about last week, trying to get cloud cover and get rain. So normally when we have a low pressure system, that's going to be our shot at getting more wet weather, more cloudy weather, maybe snowy weather. So when you hear us talk about storm systems, normally at the middle of that storm system, somewhere on the map, there's one of these L's. There's one of these areas of low pressure.
We've got David from Asheville saying hello.
Hey David, thank you very much for tuning in. So now I want to show you some of the fun stuff here when we talk about air pressure. And this is related to the atmosphere, not exactly what we're just looking at here, but this is a way that we can really see air pressure changing. This is called Bernoulli's principle. Now I think I first learned about this in 6th grade. So if you're younger, if you're still in elementary school, this is probably something you haven't talked about, but you can see it really easily. What Bernoulli's principle says is that air flowing faster than the air around it is lower in pressure. So here, put up some words for you, kind of describe that a little bit better. As the as the speed of the air increases, the pressure decreases. So we've got low pressure in the middle here where this is racing along, high pressure on both sides of it. So high pressure is actually kind of building on the outside for us. So what I want to do is try and recreate that. And here are a couple things that you can do pretty easily at home. Let me get some of these out of the way. This again is to show high and low air pressure, and we call this Bernoulli's principle. And it does relate to the weather. I'll talk about exactly how in just a second. So, easy one for you to do at home. I use colored pencils. You could use markers, anything that's going to roll. And two empty at low pressure in the middle, high pressure pushing in on the outside. So what I'm going to do is kind of set up these pencils so that they'll roll a little bit for us. And I'm going to take these two cans, they're empty, and sit them on the outsides of it. So now to try and create this, that flow of the air pressure, to decrease it in the middle, I'm just going to take a straw and blow right in between the two. So Brent, just make sure I'm not blowing on you, but what I want to do is show you two different spots here. I'm going to blow right in the middle, and let's see if anything happens. Nothing, right? The cans don't move at all. If that happens to you, just take a little bit of a step back and blow from farther behind the cans. Now watch this. Oops, a little too far. But you'll notice that pressure in the middle gets lower. The high pressure on the outside actually pushes these two cans together. Let's see if I can do a little more control this time. There you go. That's a really easy one to do at home. And what we did was just create this effect right here. We had lower pressure in the middle, higher pressure on the outsides, and that's what pushes the can in there. And if you think about it, it kind of makes sense, right? This air moving really quickly going through here, something needs to come in and replace it. And that's what's pushing in here from the sides. Let's do it one more time, see if we can get a, and again, if you are too close like this, your airflow is not going to do what you need to. You need to take a little bit of a step back. You ready? Really easy one to do at home. Now, what I like to do is kind of scale it up little by little. We had that one there. Now what we have is going to be a hairdryer. We're going to do the same thing, and this is probably something you might have at home. You've got your hairdryer and then a ping pong ball. That's probably the best one to do it. So of course, it's the same sort of thing as me blowing through the straw, but instead this time, up out of the top, the air in the middle here is lower pressure, and on the outside, high pressure is building in. So I'm going to take my ping pong ball, let's see if we can get it to, and it stays right there in the middle. But you notice if you look closely, and hopefully you can hear me, if you look closely, the ball is kind of going back and forth from side to side. So what's happening here is it's stuck in the middle of that low pressure area. It gets over to this side at high pressure, pushes it back in, and on the other side it gets pushed back in, so it just kind of oscillates or goes back and forth between the two. What's the neatest part about this, and the more powerful your hairdryer, the better it's to work, is that it'll float in there, kind of gets to a spot where it's a little bit happier, and then you can take your hairdryer and turn it to the side too. And it stays right in there. The high pressure pushing on both sides is able to hold it up at least to a point, and then gravity takes over. So let's do one more time. Kind of get it there into a good spot, and tilt to the side. And you can see there, whoop, kind of wobbling right through. But again, that is what we call Bernoulli's principle. So we kind of did it here with our soda cans. We did it with this. And last, we just kind of keep getting bigger and bigger here, is we're going to do it with a leaf blower. So now, because we have so much more power, we're going to do our giant globe kind of beach ball. If you have an even stronger leaf blower, you can actually do it to make that work. But let me do this. It is going to get loud, so I'm just going to do this briefly here. If your volume's up too high, get ready for that. All right, let's turn this on. Same idea, because we have this air flowing faster going up around it, we end up with low pressure in the middle. That high pressure on both sides holds it in place. Is when we're talking about thunderstorms and hail, where we have really powerful updrafts, that air rising really quickly inside the thunderstorm. We end up with this same sort of phenomenon, and that's where we get hail from. Before we show you that, let's see here, I'm going to try and take this back off. Let's see if we can get the basketball to work here. It worked a little bit earlier. All right, ready? So that one doesn't work quite as well. Obviously, the basketball, see, it just kind the two. Again, the stronger your leaf blower is, if you do want to try this, the more things that you'd be able to hold up higher in there. So we looked at 3 different sizes. There we have. How does that play into hail? And that's exactly what we're going to see here. We talk about the Bernoulli effect, kind of holding that hail up in the storm. So how does hail form? We've got our thunderstorm, all this air racing up into it. So that's what we call our updraft. And what happens inside of a big thunderstorm cloud is we've got ice, we've got raindrops, and the lift here, those updrafts, will hold that rain up higher in the cloud. What happens is it kind of bounces around just like our ping pong ball did, and it goes up and down in the cloud, going back below freezing and then back above freezing. So we have this really cold area higher up in the cloud. So as our updraft kind of holds that up into the cloud, it keeps going back and forth. Again, just like that ping pong ball did with the hairdryer. And eventually, it gets too much ice on it. We get more and more layers of ice on our hail as it goes up into the cloud, and then it becomes too heavy and comes down. So when you get hail in a thunderstorm, sometimes we get just maybe pea-sized hail, really little ones, a whole bunch of them. That's because the updraft is just not as strong. It can't hold the hail up in the cloud. When we get those really powerful thunderstorms and much larger hail, that's because our updraft is so much stronger. It's able to hold up heavier hail, and it can continue to do this little loop and get bigger and bigger. So it kind of starts off as a pea size, maybe turns into a penny, a quarter, ultimately a ping pong ball, and even up to grapefruit size hail in those strongest storms. So that is kind of that is one way the Bernoulli principle applies to weather. The other one is when we talk about the jet stream, kind of that same thing. We end up thanks to that air racing overhead. I believe that here is the last graphic. Fun stuff, the easiest one you can probably do right now is just with that glass of water and putting some sort of index card or something over top of it. Flip it upside down, and you can see the air pressure holding up the card in the water from underneath. Remember, so about that much space, we've got about 15 pounds of air pressure sitting on it, so it's easily enough to hold that water up in the glass. Now, if you had a super tall glass, then it would be a different story. That water would weigh too much for it. So just something you can kind of mess around with. The cans are really easy. You can also do this if you've got 2 balloons. You can tie balloons and then hang them from a piece of string and let the balloons kind of fall down. And if you blow in between them, the balloons will kind of come together just like these cans did. All sorts of different ways you can do Bernoulli's principle. If it's something that the kids find interesting, just feel free to Google some other ideas, Bernoulli's principle experiments, and you'll see all sorts of ideas, some that are really easy to pull off too. Here, let me go back to it. It is that one right there. Bernoulli's principle is that's the more fun way to play with this. I'll go back through the Facebook Live, try and get a chance to check some of them out. But when we talk high pressure, low pressure, and we're thinking about our weather maps, typically, our high pressure is going to be our nicer weather. Our low pressure is going to be our better shot for rain, cloud cover, and some storms. And the biggest reason for that, high pressure creates this sinking motion, and low pressure on the flip side creates the rising motion that we need to get cloud cover and to get thunder, or to get rain and maybe snowstorms as well. All right, that just about does it for me. I got a lot to clean up before we have our shows later this afternoon. So if you guys have any questions, anything coming in, Brett, I need to... Cool, perfect. Well, guys, thank you so much for tuning in. Next week, the plan is to talk about tornadoes. Again, we'll be back here right at 1 o'clock on Wednesday afternoon, right here on the Watch Fox Facebook account. So hopefully you can tune in and join us then. I'm Chief Meteorologist Josh Knight. Thanks again for watching.